So let us now implement the backpropagation through time. And I divided this chapter in two parts. So the first part is explaining the mathematical background. And the second part is how to convert the math into actual code. So let's take a look at the problem first of all. So we have our cell, and you saw it is actually relatively complicated or complex. And we have to set up the entire backpropagation. And what helps again, if you just actually, if you don't worry too much about it and just take a look at the good old gradient descent and then just do the math. And let's do that together. So what was the idea of gradient descent? And if you don't know the details, I would refer to my previous lectures where I explain gradient descent in more detail. For example, you look at the lecture ANN from scratch. But I still want to explain the overall idea a bit. So we have the loss function L, and the loss function in our case is the discrepancy between the predictions y hat and the actual data y we use for training. So we calculate the difference, and this is our loss function. And the loss function depends on all the different learnables. Let's call them M. And let's pick one particular learnable mj, because the loss function is highly dimensional, so it's very complex, and we can't just plot this. So therefore, let's say we only take a look at the change of the loss function with respect to one particular learnable mj. And then gradient descent delivers us this equation where it says the change of the learnable delta mj is proportional to the gradient of the loss function and the gradient with respect to the corresponding learnable. So also want to illustrate this. So if the gradient is negative, it just goes down in the loss function here. So the new value of mj is larger than the previous one. So the change is positive. And if the loss function, if the gradient goes up, the change is negative, so that it automatically goes to a minimum. And ideally, this is a global minimum. And we discussed all about these problems, how you can, in principle, also can get stuck on a local minimum in the lecture ANN from scratch. So, but for now, let's say, okay, we have this method gradient descent, and we have our loss function. And of course, we have to define the loss function. And whatever the loss function is, we have to calculate the gradient of the loss function, the derivative, with respect to the corresponding learnable. And of course, we have to do this for all the learnables. So in our case, the loss function is just the difference between y hat and y. But in principle, so for those who know physics, so the loss function can be any term which is an action term in principle, if you like. You just have to minimize a set of terms, so to say, giving some constraints. So in principle, it's kind of equivalent to the Lagrangian. In our case, it's pretty simple. So this is just the loss function. We have the difference y hat and y, and this difference dy is, of course, a function of all these different learnables. And in our case, it's quite a few. So we have 12 learnables in our standard LSTM cell. And as you have seen in the previous chapter, our cell does not has y hat as a direct output. So y hat will be passed on to a dense layer, and the dense layer converts the state vector h into a vector with y hat. So our change dy does not go directly into the LSTM cell, it goes into our dense layer. And we also have created this dense layer already in the previous lecture. So here also would refer to the lecture ANN from scratch, where we create the dense layer with the forward part, so the forward method and the backward method, and where it also creates the inputs, which are the derivatives. So this part is already done. So we just use the dense layer, the backpropagation part, so the backward part of the dense layer, which gets dy as input. So that will be d values in the dense layer. And based on the d values, it will create the input, which is the multiplication of the inner derivative you have in the dense layer with the outer derivative dy. So this is already the product of those derivatives. And this will be the input for our LSTM cell. And now we have all these different gates, the forget gate, the input gate, the output gate, and that I just called z tilde. And we have lots of learnables, and now we have to take a look at the equation. So how do all the learnables depend on each other? So that is the trail, so to say, of the derivatives, how it goes into our LSTM cell. And now let's take a look at our LSTM cell itself. And let's start with the forget gate, which is highlighted in yellow here. So I'm going to do this for every gate so that you really see where the information comes from. So where does the feedback go from HT through the different gates? And in our case, it's the forget gate. So we're starting here. In the forward part, it goes through our sigmoid function, will be multiplied with CT. Then also something will be added, which for the derivative is not important. And then it produces CT, and it also produces an output for the output gate, and then finally HT. And again, the change, so the feedback we get from the loss function goes actually through the dense layer first, and the dense layer creates the inputs as an output. And this is the derivative we have to use and multiply of all the inner derivatives in our cell here. So we have to then calculate how H would change as a function of the learnables. And let's start with UF, so with the learnable U in the forget gate. So therefore, we just have to apply only the chain rule. So we just calculate the outer derivative. And if we just take a look at the equation here, so first of all, dHT itself is actually already given by the d values that we get from the dense layer. So we just get this particular input already from the dense layer. So, but then we have to go to this equation, how H depends on CT, because CT depends on FT and FT depends on UF. So we have to go all the way back, and we have to start with the outer derivative of the tangents hyperbolicus. So dH, the tangents hyperbolicus, times dH at the tangents hyperbolicus dCt, because we have FT and CT. So what are the derivatives? So the first derivative is the outer derivative of the tangents hyperbolicus, and then we multiply this with the inner derivative. And this is what we already do in the backward part. So dHT is the outer derivative. And in the backward part, we have this 1 plus input squared, which is the derivative of the tangents hyperbolicus. So we multiply this with the inner derivative we have in the tangents hyperbolicus, and the product is the d inputs. So this is already this part here. And HT, if we calculate the derivative with respect to UF, is constant to OT. So we also have to multiply this with OT. And that's what we're going to do in the next step. So we take the derivative, which is the output here, and multiply this with OT. And it is an element-wise multiplication because it was an element-wise multiplication in the forward part. So that's the reason why we use NP multiply and we do not use NP dot. So the next step is the derivative with respect to FT. So it's dCt dFt. And CT minus 1 does not depend on the learnable UF. So we also multiply this with CT minus 1. So this is just CT minus 1. So we just take the derivative what we get here, which is the product of all those derivatives here, and multiply this with CT minus 1. So this is what you see here. Then we have all those derivatives here already. So this is this part. Then we continue with the derivative of ft itself. And ft, of course, is a function of sigma. So we have to calculate the outer derivative of sigma times the inner derivative. And in the same way we did it with the tangents hyperbolicus, we do this with the sigmoid function. So we have the outer derivative, and then we multiply this with the inner derivative, and that gives us the inputs. Also here, since in the forward part, we always have different input values for the tangent hyperbolicus and the sigmoid function, we had these different instances. For every instance, so for every time point, we have an instance where we have the output, and we use the output for calculating the derivatives in the backward method. So therefore, we have a t here, and we have a t here, so that we have, so we multiply with the inner derivative, which really corresponds to the time point t. So we have the outer derivative, which we have here, multiply this with the inner derivative of the sigmoid. So we just performed the multiplication of all these terms, and this is the output here. So this is product again of all these derivatives. And now finally we calculate the last inner derivative, which is the sigma the UF, which gives us an xt. So we just multiply this with xt. This time it's an NP dot because it was really an actual matrix product. And then we know what the change of UF is. So we just say UF plus all the derivatives. Why is it plus? Because we have one cell still that gets the information from all the time points. So whatever the feedback is, all the time points contribute to the change of UF. It can be positive for some times, it can be negative for some time points, but overall it just adds all those values up. So that is the backpropagation for UF. How does it work for all the other learnables? Well, once we have all these outer derivatives, and for example, if we want to switch to WF, we can actually keep all the code that we have here already, because the only difference is the inner derivative at the very end. So we have all those values here, which is d sigma f, and now we just multiply this with the last inner derivative, which gives us an ht minus 1. So we just multiply this with ht minus 1. Just make sure that the shapes work. So in this case, we have to transpose it. And again, for every time point, the derivatives contribute to the learnable, which is WF in this case. Well, and then you do the same for the bias, but the inner derivative gives you just a plus 1. So we just can add up the derivatives you get from the sigmoid directly. And this is essentially the trail that goes through the forget gate. And then we have all the derivatives for the learnables in F. So let's go to the input gate. Also here, I want to highlight this in yellow that you really see how the backpropagation goes through our LSTM cell. So how does it work? In principle, it's the same idea. So there's no difference. So we just calculate the derivative now with respect to UI. And we have the derivatives here, which are highlighted in blue already, because we had to pass the tangent hyperbolicus first. So now we calculate the derivative with respect to IT, because IT contains UI. So it's dc, dIT, and it's constant with respect to c tilde. So we multiply the derivative that we have here with c tilde. And we multiply this again element-wise because it has been generated element-wise in the forward part. And then we multiply this with the derivative from the sigmoid. And again, with the last inner derivative, that gives us an xt. And again, all the time points contribute to the derivative. For WI, it's again the same structure. The difference is just that we have an ht minus 1 at the end. And again, for the bias, the derivatives gives us a 1. So we just add up the last derivatives. It's a bit different now for UO, because now we have to calculate a derivative with respect to OT, so the output gate. So therefore, the tangents hyperbolicus that we have here in HT is constant with respect to UO, WO, and BO. So we have to calculate the HDO, but then multiply this with tangents hyperbolicus CT, which is the output. So we have the DHT, the values, then we have to calculate this derivative here. So it's DHT, but then multiply this with the output from the tangents hyperbolicus here. And then we pass it on to the sigmoid, because DHDO is actually the outer derivative of the sigmoid. So we directly pass it on to the sigmoid, and then we calculate the derivative, the sigma, and this the inner derivative, times the last inner derivative, the sigma d UO, and this gives us xt. So we have the outer derivative, the inner derivative of the sigmoid already. So we have the product of this part, so we just have to multiply this with xt. And then it's completely equivalent for WO and for BO as well. All right, so that's almost it. Of course, we have to do this for C tilde as well. Again, we just follow the derivatives. So C tilde is, so CT is a function of C tilde. So we have to take this derivatives from the tangents hyperbolicus we have earlier, then times the inner derivative times the derivative of C tilde. C tilde is multiplied with IT, so we have to multiply this with IT element-wise, and then the inner derivative of the tangents hyperbolicus times xt, and for WG it's times HT minus 1, and for the bias it's again just adding up the last derivative, because the inner derivative, so the innermost derivative, just gives us a 1. All right, so now we have the derivatives of all the learnables, but we still have to calculate the derivative of h. So how does h actually change with respect to time? Because remember, DHT was an input argument in the first place. So we have to calculate DHT. And if you look at our cell, we actually have to take two terms into account. So the first term comes from the previous cell. So this is really how HT changes with respect to HT minus 1. And this is this part here. So where we have the derivatives from the learnables. So we have to multiply this with the learnables, which are connected to HT minus 1. So this is really the information from the previous cell. But these are the inner derivatives. We also have to multiply this with the outer derivatives, and we have all these outer derivatives already. So this is DHT, how it changes with respect to the information of the previous cell. But there's some information missing. That's the information of the current HT, which comes directly from the loss function. So we also have to calculate or add the change from the loss function. Remember what the loss function was. So we do not have the direct output from the loss function. We get it from the D inputs from the dense layer, which will be the D value. So this is the outer derivative. So this is the direct information from the loss function, which also makes sense, of course, because in order to adjust the weights, we need, of course, the feedback from every delta y for every time point. And then we combine the information with the change from the previous cell. So we also calculate how HT changes. And because it's also been multiplied with all the learnables. So CT, we can in principle also calculate the change of CT, but CT is not a learnable. So that is the math, and now the math is complete. And in the next step, we just want to turn the math into actually code. So that we have our backpropagation part, our backward method, and then we also want to test this. So the math is done, and now we have to translate it into code. That's what I'm going to do in the second part of this particular chapter.